we're on our unit 3 right now, and I'm going to flip open to the summary right here. I've got it numbered 3, flip open to it, and I see it says mass relations and chemical reactions, which we're going to do. I've got some chemical reactions, and we're going to see what happens in terms of gravity, mass, and also a very important thing, moles. Now I'm looking here, and I hope you looked at it too, and have seen that we deal with Avogadro's number here, which is 6.02 times 10 to the 23. Now, really, that's almost a bit of trivia. You probably won't be asked for that number because it's so huge. It's larger than the number of stars you can see in the sky. When we talk about numbers of atoms, there are 10 to the 23 atoms in here. So we're not going to deal with those as numbers. We're going to call them moles. We just know a mole is a large number. It's a super dozen, if you like. And the secret is that we've got to change weights, and I've got a weight here that I want to change, into moles, into numbers of atoms, into an amount. Weight, yes, that's the amount of mass in something, but we want to know how many atoms are in there that are going to do the reacting. Because like when this magnesium reacts, it's its atoms that are reacting. We don't care how much they weigh. We want to know how many of these things are burning. So we've got to change the mass, because I mean, how many moles are in there? I don't know. There's no balance here that's going to give me the number of moles. There's a balance here, though, that can weigh it and give me grams. So we have to convert grams into moles. And you've read this already in terms of how to do that. And what I'm going to do is I'm going to do that consistently. In other words, you have seen the secret periodic table for changing grams into moles, and you've looked at their sample problems. I'm going to actually do them in a reaction. So you get a chance to see what moles are doing. Our first thing that we're going to do is we're going to check to see if we can use moles to come up with a formula. I'm going right here. Something's called empirical formula. No, you've seen formulas before. In fact, you know how to make them. You learned in our previous unit where you can predict and do formulas and also give their names. Now, we're going to pretend that, not pretend, we're going to confirm what we know already. You know magnesium, and it's a metal. So when it reacts, it's going to make an ion. And you know the charge of the ion that's produced when we make a formula. And you also know the ion oxygen, that it gains a couple of electrons. So you can predict this formula. But let's pretend that we really don't know what the formula is. Or even if you do, you want to prove it. Empirical. That's when you do an experiment to find out if what I'm teaching you is right. I hope it is. So we're going to check, what I've told you. We're going to check to find out what the real subscripts are here. Now, the classic experiment that's done is we take our magnesium and we weigh it. I've got 1 gram here. And we're going to combine it with oxygen. We're going to have it start to burn. Okay. Now it's going to be bright. The camera is going to adjust for it, but it's going to be really bright. So I'm going to get my glasses on, so I'm not blinded by the light. And I'm going to start this magnesium combining with oxygen. 1 gram of magnesium, which I can weigh. This is a crucible. They're pretty, aren't they? Like a little teacup. They even had pretty little lids. They're relatively expensive, about $5 each, if you get a discount on them. And they're made of a special porcelain. Porcelain goes back all the way to ancient China, where they were able to take special clays to make these beautiful white ceramic objects. I mean, vases made in ancient China are a fortune. It was a special formula. They kept it secret for hundreds of years. And it wasn't really until around 1600s that somebody in Europe figured out how to make porcelain in Europe in Leipzig. If it's an alchemist, he was supposed to be making gold, but he knew he couldn't, and he made some porcelain. Now, this is very thin. Porcelain can take huge temperatures without melting. If I did this experiment in a beaker, the beaker would melt. So if you want to do something at high temperatures, these porcelain crucibles are beautiful for it. And this is a high temperature. The only hazard is these things are brittle. So if I drop this, even from this height, it's going to break. I've broken my share of crucibles. In fact, every time I've ordered crucibles, there's been at least one in the shipment that's broken. They're that delicate. They have to be thin because if they're thick, the inside heats up too quickly and it expands and it cracks. The thinner your crucible, the more likely it is not to crack. So let's hope this doesn't crack. In fact, ideally, I should heat the entire crucible, but I'm not going to do that because I got to get a Bunsen burner out and set the uh oh, tongs are used to pick up hot crucibles. And they're little lids. One of the nice things about chemistry is you get to work with some beautiful equipment. Let me turn this on again, light it, and get this magnesium burning. It's going to take a little while. It's a very, very high ignition temperature. It's not easy to get ignited. Come on, come on. There it is. It's starting to burn. Isn't that beautiful? Whoops. Okay, I got to get that crucible lid on. It didn't break. Oh, isn't that beautiful in there? You can see it. I mean, that's how thin the porcelain crucible is. You could actually see the light through it. Now, when you do this experiment, ideally, you keep it hot and you keep it igniting and you let a little bit of oxygen in at a time. You lift this up, let it burn. Whoop, lift it up, let it burn. Lift it up and let it burn. It's an experiment that lasts about a half hour if you're really careful. And you're heating it with a Bunsen burner during the entire time. And this way, you trap all that white smoke. You trap all of the magnesium oxide. So you're going to know how much this weighs. Instead of having the magnesium oxide go out, you're going to have it trapped in here, and it's going to weigh more because magnesium has combined with the oxygen. Now, I'm not doing the experiment now because we have to do this for a half hour. When I'm completed with this, the weight of this would be about 1.60 grams. In this case, you're going to have to sort of say, okay, we'll presume my chemistry teacher's not lying to me, but it will weigh more. And I'm going to just check my notes here and make sure I've got everything right. Oh, actually, it's 1.65. Let me erase this. Now, if I was having a lab notebook, then I couldn't erase. I would cross it out and put this underneath it. And I'll talk more about lab notebooks when we really do an experiment. Next, so 1.65 grams. You say, well, that means the oxygen must have weighed 0.65 grams. 0.65 plus 1, they've come together. Now, how's that going to help us with a formula? I mean, I don't see a formula here or here. It looks like there's less oxygen than there is magnesium. In fact, if anything, if you're guessing right now, you'd say, okay, a bigger number here, a smaller number here. Well, where do we go from here? Periodic table time. Magnesium. Underneath magnesium, 24.30. No units are shown on the table because that could be atomic mass units. But it also can be grams per 1 mole. Oh, You may have noticed a few stains on my jacket. Well, the stuff I'm working with in this session, they're going to stain anything. In fact, you may even notice my hands have got some stains on them. I tried very carefully not to when I was preparing for this, and still they got stains. So this is my lab jacket for experiments where you're going to get your lab jacket stained, and there's no way to get the stains out. So rather than having my great jacket, I'm having this one, my working jacket, if you like. Okay. Oh, we're going back to this. 24.3 grams per 1 mole. This is a ratio. This allows you to change a weight that you get out of balance into what we really need to know, the amount, moles. And you can use this ratio that you get from any of these numbers to change an element into mass of an element into an amount. So I'm going to take my 1 gram and change it. Well, it's grams right now, and I want moles. Well, this is a ratio. You can write it 24.3 grams per mole, and that's how you usually write it because you see the 24.3 here. But you can also write it 1 mole, 24.30 grams. This is 1. This is an equality. This many grams is 1 mole, so it's 1. So I'm multiplying by 1. And you can flip it over, and it's still multiplying by 1, but this way, my grams cancel. I don't have to memorize the formula. All I have to do is know that grams per mole and decide whether to use it this way or this way. This way gets rid of grams and gives me moles because we know that cancels out. Calculator time. All right. 1 divided by 24.3. Well, I get a lot of numbers, but we're going to carry this out to 3 significant figures. Okay, this is 0.041, and I'm going to round it off to 2. It's 115, and grams cancel, so this is moles. So how much magnesium do I have? I have, in terms of magnesium, 0.0412 moles, or 41.2 millimoles if you're good at moving your decimal point 1,000, 3 places. Well, we've figured out the moles of magnesium. In fact, that's usually the first step in a host of AP problems. If you've got a mass and you've got a formula, you can convert that mass, which is misleading, to moles. Well, I've got a mass here, 0.65 grams. Now, that's only 2 significant digits, but it's oxygen. Now, oxygen atoms have 16.00. And I'm just going to write down 16.00 grams per 1 mole. Oxygen atoms are lighter. So when you have 6 times 10 to the 23 of them, instead of weighing 24, they only weigh 16. But you have the same number. So you've got an equal amount. Okay, calculator. On 0.65 divided by 16.041. 2 significant digits. Moles. My oxygen is 0.041. My magnesium is 0.041. So I have identical amounts of both. Formulas about amounts. I have here, let me write this so I can get the O in, and I'm going to erase these other things. I have 0.041, 0.041. Now I think you can see that our formula is going to be equal amounts of magnesium and oxygen. Now, the mathematical way of doing this, if you're doing this formula, the long way, you look for the smallest number and divide both of these by the smallest number to get their whole number ratio. Because we don't want 0.041. We want to scale it up to whole numbers, which is magnesium 1, oxygen 1. That's the formula. And that's the formula we predicted with the +2 and -2. So I wasn't lying to you. Even though this isn't hot, it's warm. I see this white powder in here. A good deal of it burned. By the way, that white powder is like the definition of white. Magnesium oxide is used by photographers to find out what the perfect white is. There's a lot of whites, and magnesium oxide is the ideal. And it's also used, ironically, it's used in making porcelain. If you have a brick that can withstand high temperatures, it's got magnesium oxide in it. So there's our formula, MgO. Oh, the name, magnesium oxide, because you can speak chemistry. Let me get this out of the way right now and tell you about one little twist. We got the right formula. It's the empirical formula. It's reduced to the whole ratio numbers. And for ionic materials, we do that all the time. Let's say our answer would have been this. And I'll put an X here because we know that's not so. That when we did this with a metal, we got a 1, and instead of a whole number, we had a decimal. Well, it's true. We're going to have more oxygen atoms than X atoms. I mean, there's nothing wrong with that, but we like to use whole numbers. So if you get a fraction like this, multiply it by whole numbers so that you get whole numbers. If I multiply this by 2, I get X2O3. It's the same ratio. 1 to 1.5 is the same as 2 is to 3. So should you get a problem that has a nice decimal like this, multiply to get whole numbers. Because I mean, it's much easier to write a formula X2O3, X oxide, than 1.5. Empirical formulas, you change the mass into moles. Put the moles into the formula. Divide by the lowest number to get nice numbers. And if your numbers aren't perfect, multiply so that they become perfect. It's a great count. And it's amazing that just doing a little bit of weight here, I mean, this balance, if I was meticulous enough, I could have burned that completely and figured out what the formula was. In fact, this is done all the time to figure out formulas. This is how we came up with formulas. They came up with these atomic weights, and they did it very cleverly. And in fact, using this technique too, and then said, okay, what's the formula of this stuff? I mean, you can find the formula of this experimentally, empirically. All right. That was our first part. Now for a real experiment.